Yeah, everyone. Gonna talk about Green's theorem today. All right, so before we get into what the theorem says and how to use it, um, we are gonna define something, language that's used in the theorem itself. Simply connected curves. So when we refer to simply connected curves, simple implies that the curve does not cross itself, and then connected just means that our starting point is our ending point. There are no holes, there are no separate parts. So below I have some examples of what a simply connected curve could look like. All right, so first, there's that one. That's a good example. The other two are not simply connected. This one because of the hole, this one because of the separate regions. If I were to draw something that looked maybe like a figure eight, that would also be an example of not a simply connected curve. So now that we've gotten that definition out of the way, the actual theorem itself. So Green's theorem is something that actually connects line integrals, like we've been learning about, to double integrals over a region R that essentially look like a volume problem. All right. So we can make this association, i.e., we can rewrite a line integral as this, or we can rewrite this volume problem as a line integral. The thing is, there are conditions to this. We can't do this every time that uh, we can't do this every time that we see simply connected curves. So that is one of the conditions, simply connected curve. But in addition to that, the path that we take for a line integral should be moving in a counterclockwise direction. That's pivotal to this because there's an assumption in Green's theorem that R, the region that you're integrating over for the double integral, is always to the left of the path C. All right, so um, let's do some examples. First off, let's say that we want to evaluate this line integral by using Green's theorem. So we have our path set out for us here. We are traveling from 0, 0 to 1, 1 along a cubic graph. So that's going to look like that. And then we're traveling back from 1, 1 to 0, 0 along the line y equals x. So you can see that this is a simply closed curve and it doesn't cross itself. So it's simple. It doesn't have any holes. There are no multiple parts. So that qualifies. By the way, another name for simply connected curves are Jordan curves. And if you ever study topology, that's going to have some interesting connotations later. All right, but anyway, that's what our path looks like. So we know that the conditions for Jordan or Green's theorem are met. With that said, I can actually set this up to be a double integral now over the region R, where R is the space that's enclosed by the path. All right, and then in the theorem we stated we used M and N, right? So to identify those, just look at the differential. So dx is going to give me my M. The dy part is going to give me my N. If I take my partial derivatives, and so dn dx, so partial of n with respect to x, look at that, we get 3x squared plus 3y squared. And then if I take the partial of m with respect to y, all right, that's going to be 3y squared. So the integrand from Green's theorem is going to be the difference between these two. So my partial of n with respect to x minus partial of n with respect to y. So if I subtract these, all I'm left with is 3x squared, which is pretty convenient. And now we just have to set the integral up the same way that we did our volume integrals. So one way is to just write some parametric equations. We don't even really have to do that. Like, yeah. We can set this up like, we don't even have to write parametric equations. We can just set this up like a regular area volume problem. So if I were trying to find the area of R, remember we would have one set of bounds be the top and the bottom curve. In this case, my top curve is going to be y equals x. So that's my top bound. My bottom curve is going to be y equals x cubed. So that's the bottom bound. Keep in mind that since these are x's, we have our path defined as y in terms of x. We want this to be the inner integral, and we want our first differential to be dy, because remember, if x is part of the bounds, dx cannot be your differential. So that said, because we're doing this in terms of x and y, my dA is just going to be dx dy or dy dx, whichever one we need. And then for the last part, we need values of x. So I noticed that everything in this path, the x values range between 0 and 1. So those are going to be the bounds for that outer integral. Squared. There we go. So then when I take my integral, remember you start from the inside, my antiderivative is going to be x cubed. I'm going to evaluate that from, not x cubed, whoops, 3x squared y. And that makes me thankful for the Doppler effect. All right. So then if we subtract our bounds, the integrand will become 3x squared times x, so known as 3x cubed, minus 3x squared times x cubed, also known as 3x to the 5. So this is going to end up working out to 3/4 x to the 4, add 1 to the power, divide by the new power, minus 3/6, which reduces to 1/2 x to the 6. We'll evaluate that from x equals 0 to x equals 1. Note, if you plug 0 in, you're going to get 0. All right. But if I plug 1 in, I get 3/4 minus 1/2. And that's going to result in my answer, 1/4. So that was one example of how we can take a path integral, a line integral, and convert it to something like an area problem that we talked about really early in the multiple integration chapter. If we look at another example, we can see this in a different context where perhaps we might actually use a different coordinate system when we set up the integral. So if I can find my green. Okay. Write out the next example. So our next example involves a problem where we calculate work. So remember, to do this one, we need to know our force field. So force F is given to us as the vector y cubed I plus x cubed plus 3xy squared j. All right, and we're traveling around a circle with a radius of 3. All right, and we want to use Green's theorem to calculate the amount of work done by this force field. So So essentially, if I wanted to figure out the work done by this force, I could set up a path integral over the path C. We're going to be moving around a circle in a counterclockwise direction, right? Because we need Green's theorem to work. All right. And essentially the integrand for this, because of the way that the force field is written out here, I can write this as y cubed dx, because that's the I component, plus x cubed plus 3x squared y, or 3xy squared, I mean, dy. So this is the work that is done by the force field written out as a line integral. Because of Green's theorem, first off, it's a circle. I know circles do not cross themselves. I know circles don't have holes and don't have separate parts. So we know that C represents a smooth, simply connected curve. It also is smooth because its derivatives are continuous. So I know that I can use Green's theorem to rewrite my line integral as the integral over the region R, which is enclosed by the circle, of the partial derivative of n with respect to x minus the partial derivative of m with respect to y dA. All right, but before I write all that out, let's find these partial derivatives. So partial of n with respect to x. All right, my n is going to be the second piece right here. If I differentiate with respect to x, get 3x squared plus 3y squared. If I look at my m, remember that's your x component. If I differentiate this with respect to y, I get 3y squared. So the integrand for this integral for Green's theorem is going to be the difference between these, this one minus this one. If I do that, I'm going to be left with just 3x squared as we were in the last example, and dA. So one major difference about this region R is that we're looking at a circular path. All right, so if I were to just draw this circle out, I have a circle, we have radius 3, we're going in a counterclockwise direction. Think of it this way. If I were to cut off at various values of t, I would get sectors of this circle, right? So the region R that I'm using in this area volume setup is not just a straight up rectangular or rectangle-like region, right? It's more of a pie slice region. Remember, when you have something that's more of a pie slice region, it's better for you to use polar coordinates if you're looking at 2 variables, or cylindrical or spherical if you're looking at 3 variables. So in this case, we would use polar coordinates to set up the dA part. So that said, we know that in polar coordinates, a circle of radius 3, by the way, we're going to do the entire circle, not just that region. This was illustrative. Right? So I know that to set up this integral, write it again over here. All right, I'm gonna have my bounds involve r, the radius, and theta, the angle. So we have a radius of 3, meaning r is going to range from 0 to 3. We're going around the entire circle. So theta is going to range from 0 to 2 pi. The integrand is 3x squared. Remember, we have to convert this to be in terms of r and theta. So using this definition, polar coordinates, x is r cosine theta, we can rewrite this as 3 r squared cosine squared theta. And dA, the differential in polar coordinates, remember, was r dr d theta. Remember, you have a Jacobian here that's not just 1. So simplifying this a bit, I'm going to take the 3 out. I'm going to multiply the r's together. So we're evaluating this double integral. First with respect to r, then with respect to theta. So start in the middle. I notice the r part, I can use the power rule to get my antiderivative. So we have 3 integral from 0 to 2 pi. My antiderivative will be r to the 4 over 4, but I can pull that out front with a constant. And then the cosine squared theta is unaffected because there's no r in cosine squared theta. Then we're going to evaluate this from r equals 0 to r equals 3 and integrate with respect to theta. So if r equals 3, 3 to the 4 gives me 81. All right. And then if I plug in 0 for r, that whole term will be 0. So I get the integral of 81 cosine squared theta. It would be in my best interest, though, to take this 81 out front with this constant. If I multiply 81 times 3, I get 243. And we still have our over 4. So now we have to integrate cosine squared theta d theta. To do that, we would need to reduce the power on our cosine squared theta. Remember, we can do that by using our cosine double angle formula, right? Power reduction formula, whatever you want to call it. So remember, cosine squared theta can be written as 1/2 times 1 plus cosine of double theta. So the 1/2 I can bring out front, multiply it by the coefficient I already have there. And my integrand will now just be 1 plus cosine of double this angle, which is very doable. So at this point, if I multiply these coefficients together, I get 243 over 8. Then taking my antiderivative of 1, I'll get theta. Antiderivative of cosine, remember, is positive sign. And because of that coefficient, we have to divide by 2. So plus 1/2 sine of 2 theta. And we're going to evaluate from theta equals 0 to theta equals 2 pi, which is pretty convenient in this case. So first off, we know that this theta term, if I plug in 2 pi, it's 2 pi. If I plug in 0, it's 0. 2 pi minus 0, we get 2 pi. So I have my 243 over 8, I'm going to multiply by 2 pi. Now, if I do the same with this sine term, remember sine of 4 pi is 0. Sine of 0 is also 0. So this term is literally just 0. So lastly, if I multiply this, I can actually simplify 2 over 8 to be 1 over 4. Multiply by the pi, and I get 243 pi over 4. And that's our answer. That is the amount of work that's done by that force over that path. And we didn't even have to do a line integral. All right. So next, what happens, or how do you think the problem would end up working out if I had a spiral notebook that could flip pages easier? There we go. So what do you think would happen if I had a vector field that is conservative? Well, here's the thing. The way that we're rewriting these line integrals should definitely make you think of something that we've seen before, right? Remember our test for 2D vector fields to see if they're conservative? remember we had to find the partial derivatives with respect to each component. This is the exact same thing, except instead of looking at something written as I and j, we're looking at it written as dx and dy. So if I look, so let's say that we want to evaluate the following line integral. So we have integral over the path c of y cubed dx plus 3xy squared dy. All right, and c can really literally be any simple closed path that's going counterclockwise. So if I let c be any path where Green's theorem applies, then we know that we can rewrite the line integral as just a regular double integral. All right, but before we do that, we want to look at these partial derivatives. So first off, if this is a conservative vector field, what are we going to notice about the partial derivatives? And if it works out the same way that it did when we're looking at vector notation, then we would expect to get the same thing for each partial derivative. So if I start off with my partial with respect to x of n, all right, so I'm going to look at the dy piece. If I differentiate with respect to x, I get 3y squared. Okay, now if I take the m piece, right, so whatever's in front of dx, and I differentiate with respect to y, again, getting a mixed second partial derivative, then, yep, then I'm going to end up getting 3y squared as well. So because these partial derivatives are the same, right, that's equivalent to saying that this represents the gradient of something, therefore, we could use the fundamental theorem of line integrals since this is a closed path, and we can use the fundamental theorem of line integrals. That implies that this integral is equal to 0. All right, but if we take the Green's theorem route of writing that out, we know that we're going to take the double integral over the region R that is enclosed by the path C. The integrand is going to be partial of n with respect to x minus partial of m with respect to y dA. Since these two partial derivatives are the same thing, when I subtract them, I'm going to get 0 for every xy pair that I can think of. So we get 0. That's it. All right. So again, another really nice, convenient, thing that we see with conservative vector fields. Okay, so next, I want to do that one. Okay. So next, we can actually use Green's theorem to kind of do the opposite, where we start off with kind of a double integral where our intent, right, that's the word, is to set up an integral that calculates area. Right, so that's remember the double integral over r dA. Right, we can actually use the result from Green's theorem to make this into something that is a little more manageable, perhaps. And here's the formula. So this is our area using Green's theorem. So the area of a region that is enclosed by a simple closed path, simply connected path, is equal to 1/2 times the line integral over that path C of x dy minus y dx. All right. So an example of that, right, as an example, let's say that we want to use a line integral or a path integral to find the area of an ellipse. So find the area of the ellipse given by this equation. Okay. So using the formula that we got to compute area using a line integral, we can kind of just set this up willy-nilly if we want. So we know the area is going to be given by 1/2 of the integral over the path C that encloses the area that, in other words, is going to be this guy, of x dy minus y dx. Okay. So to evaluate this line integral, we have to go back to some of the stuff that we did in the last couple of videos, right, where we write parametric equations. So for an ellipse, you remember way back from the earlier chapters, we can write parametric equations for an ellipse as x equals a cosine t and y equals b cosine t. Right here, a and b are just the radii for each axis that we can get from the equation. So with that said, we can figure out values for dy and dx just by differentiating these. And yeah, so dx I can get by differentiating this similar to how you would for a u sub. So a is a constant, derivative of cosine is negative sine. So we get minus sine of t dt. And then for dy, differentiate this. Oops, it should not be cosine, it should be sine. There we go. All right, so for this one, differentiate sine with respect to t, you get cosine. Oops, should be an a in front of that one. So b cosine of t dt. Now that we have expressions for x, for y, for dx, and for dy, we can completely set up the entire line integral. The only other thing we have to think about is what our values of t are going to be. And thinking about it, because we're going all the way around an ellipse exactly once, we know that t is going to range from 0 to 2 pi. So I can use those as the bounds of that integral. So we get 1/2 integral from 0 to 2 pi. Then we can replace the x with a cosine t and dy with b cosine t dt. All right, then our y we can replace with b sine of t, and dy or dx we can replace with negative a sine of t dt. So if I multiply everything out, I get ab cosine squared t. Right, the dt's I'm going to kind of factor out and put at the end here. Minus negative, so plus AB sine squared t. All of that with respect to t. So at this point, we should notice that we're going to be using that same trig identity from before. So we're going to factor the AB out. Since these are constants, we can actually pull them all the way out of the integral. And we're just taking the integral from 0 to 2 pi of 1, right? That's sine squared t plus cosine squared t dt. Meaning that I'm going to get AB over 2 multiplied by 2 pi. In other words, AB pi. So AB pi would be the area of the region enclosed by that ellipse. Okay. So with that said, there are alternative forms of Green's theorem that we can also look at that kind of relate it back to some of the other things that we covered. Yeah. But I'm going to hold off on it because a lot of these same concepts are going to come up when we talk about Stokes' theorem later on. All right, so with that said, the big idea with Green's theorem, if certain conditions are met, namely the path that you're integrating over is a simply connected curve, i.e. a Jordan curve, and is going counterclockwise, we can rewrite line integrals as regular double integrals, or we could rewrite regular double integrals as line integrals. And a result of Green's theorem is that there's a way for us to find area enclosed by a path, right, by doing a line integral over that path. And that's pretty much it for Green's theorem. Happy mathing.